Imagine a smartphone battery that charges in seconds and never degrades, or an aircraft wing lighter than a feather but stronger than titanium. Consider a medical implant that perfectly mimics human bone, seamlessly integrating with your biology without a single hint of rejection. These are not distant science fiction fantasies. They are the imminent realities of a world where the fundamental building blocks of our physical environment are being reimagined from the atomic level up. For centuries, human engineers have relied on a painstaking, deeply physical process of trial and error to invent new alloys and compounds. Thomas Edison famously tested thousands of materials before finding the right filament for his incandescent light bulb. This slow, methodical approach has historically defined the absolute limits of human progress, tethering our grandest architectural and technological ambitions to the sluggish speed of manual laboratory experimentation. The echoes of those early trial and error days still guide the field, but the laboratory itself has fundamentally changed. We are no longer confined by the limitations of human patience or the physical constraints of a traditional workbench. A profound shift has occurred, moving the crucible of creation from the physical bench to the limitless expanse of the digital realm, forging a new binary bridge between human intent and vast computational power. Enter the era of generative AI, a technology that completely flips the traditional script of discovery. In the realm of materials science, this artificial intelligence does not merely produce text or generate images, it performs the astonishing feat of atomic structure prediction. By analyzing the fundamental laws of physics and chemistry, these algorithms can simulate millions of hypothetical combinations in the time it takes a human researcher to pour a single cup of laboratory coffee. These sophisticated systems ingest massive datasets containing the known elements and all existing compounds. They map the incredibly complex relationships between microscopic atomic arrangements and macroscopic material properties, such as conductivity, elasticity, and thermal resistance. Through this deep analysis, the machine learns the hidden grammar of the physical universe, allowing it to propose entirely novel compositions that no human mind had ever conceived or documented. The immediate result is a staggering R&D cycle acceleration that is sending shockwaves through global industries. What once required decades of meticulous synthesis, exhaustive testing, and endless refinement is now being compressed into mere days. This unprecedented speed is fundamentally reshaping engineering and manufacturing, shifting the entire paradigm from discovering what already exists in nature to designing made-to-order substances engineered for highly specific, critical applications. Consider the desperate global quest for better, cleaner energy storage. Researchers at leading institutions, like the Lawrence Berkeley National Laboratory, are utilizing these advanced AI models to sift through billions of potential molecular structures to find the perfect solid-state battery electrolyte. The algorithm identifies unique candidates that maximize energy density while minimizing the risk of thermal runaway, effectively designing the safe power sources that will drive the next generation of electric transportation. Yet the machine does not work in isolated autonomy. The true magic of this technological leap lies in the intricate, collaborative dance between human scientists and their digital counterparts. Human researchers establish the safety constraints, define the desired material properties, and carefully guide the algorithmic parameters. We provide the ultimate destination, and the artificial intelligence maps out 1,000,000 possible routes to get there, highlighting the most efficient paths forward. But what if the algorithm hallucinates a structure that cannot physically exist outside a computer simulation? This is the fascinating friction point where digital dreams meet physical reality. An AI might design a theoretically perfect, indestructible alloy that requires conditions hotter than the center of the sun to synthesize, rendering the brilliant digital discovery practically useless for any real-world application on Earth. The real challenge lies in bridging this gap between a flawless digital prediction and a tangible, physical synthesis. Unlike a software bug that can be patched with a few lines of code, a failure in materials science means a physical compound crumbles, shatters, or simply fails to form in the beaker. The digital pioneers had set a course, but the physical world demands rigorous, uncompromising, real-world validation. To solve this complex bottleneck, the binary bridge expands to include highly automated robotic laboratories. These autonomous, glass-enclosed facilities act as the physical hands of the AI mind. Once the generative model proposes a promising novel composition, the robotic systems take over, precisely mixing, heating, and testing the AI-generated recipes around the clock, operating without fatigue or the biological need for sleep. This closed-loop system is a marvel of modern automation and machine learning. The robots synthesize the material, test its electrical conductivity, tensile strength, or thermal resistance, and immediately feed that physical data back into the neural network. If the material fails to meet the predicted standards, the AI instantly adjusts its internal understanding, learning from the physical failure to rapidly refine its next batch of digital predictions. This continuous, self-improving loop is accelerating material discovery at a pace that is almost difficult for the human mind to comprehend. Recent breakthroughs by deep learning models have proposed hundreds of thousands of stable crystal structures, effectively expanding humanity's catalog of known materials by an order of magnitude, adding over 2.2 million new possibilities in a single bound. The sheer volume of these discoveries represents a treasure trove of potential technological revolutions. As this immense digital catalog expands, the role of the human engineer is undergoing a profound and permanent evolution. We are transitioning from manual laborers at the lab bench to high-level orchestrators of immense computational power. The human mind is freed from the tedium of repetitive testing, allowed instead to focus on the ethical implications, the overarching strategies, and the creative application of these newly birthed substances. Leading materials scientists now speak of an impending future where we no longer search for materials to fit our designs, but rather dictate our design needs and have the perfect material generated on demand. This shift transforms materials from a limiting factor into a highly dynamic variable. If an aerospace engineer needs an alloy for a Mars rover that is 20% lighter but twice as radiation resistant, the AI simply calculates the required atomic structure. In the critical, high-stakes realm of biotechnology, this predictive capability is genuinely life-saving. Artificial intelligence is accelerating the discovery of novel polymers and hydrogels that can perfectly interface with delicate human tissue. By predicting exactly how different molecular structures will interact with biological cells, AI is enabling the creation of smart medical implants that actively promote healing, dissolving harmlessly into the body once their structural job is complete. However, this blistering pace of invention forces us to confront complex new questions about global resource allocation and environmental impact. When we can invent thousands of new materials overnight, we must carefully consider the heavy ecological cost of synthesizing them at scale. Are the rare earth elements required for these new superalloys ethically sourced? Can these highly complex AI-designed materials be effectively broken down and recycled at the end of their life cycle? And this is just the beginning of a profound transformation in how we interact with the physical world around us. The algorithmic shadow now looms over every major industrial breakthrough, promising unprecedented solutions to some of humanity's most pressing challenges. From capturing carbon directly from the atmosphere to purifying ocean water with unmatched efficiency, the materials required to save our planet may currently reside in the latent space of a generative model. As we look toward the technological horizon, the integration of quantum computing promises to deepen this predictive capability exponentially. While current classical computers simulate atomic interactions using clever mathematical approximations, quantum computers will eventually possess the power to model the exact quantum states of every single electron in a complex molecule. This massive leap will eliminate the remaining guesswork, allowing for the flawless prediction of material properties before a single physical atom is ever moved. The contrast between our historical past and our impending future is stark and undeniable. We are moving rapidly from an era defined by what we could accidentally discover in the dirt to an era defined by what we can intentionally design in the cloud. The slow generational accumulation of metallurgical knowledge has been replaced by the blistering speed of algorithmic iteration, forever altering the timeline of human innovation. Yet amidst this blinding technological speed and autonomous synthesis, the human element remains the vital, irreplaceable anchor. It is human curiosity that asks the profound questions the AI attempts to answer. It is human empathy that directs these massive computational resources toward curing diseases, mitigating climate change, and improving the daily lives of people around the globe. The machine provides the complex how, but humanity must continuously provide the moral why. The societal implications of this structural shift will eventually touch every single aspect of our daily routines. The buildings we live in, the vehicles we travel in, and the tiny digital devices we rely on will all be fundamentally upgraded by materials that are vastly stronger, incredibly lighter, and far more sustainable. We are standing on the precipice of a new material age, one not defined by stone, bronze, or iron, but by the limitless potential of artificial intelligence. The hard-learned lessons from that early laboratory research never faded. They were simply digitized, categorized, and amplified. Every failed experiment of the past 3 centuries has become invaluable training data for the algorithms of today. The collective physical struggle of generations of scientists has been distilled into mathematical weights and biases, creating a digital inheritance that empowers the machines to see further into the atomic realm than we ever could alone. We must prepare for a world where the traditional physical constraints of engineering are continually shattered and redefined. The everyday materials of tomorrow will seem like pure magic to the engineers of today, blurring the increasingly thin line between physical reality and digital imagination. This is the ultimate promise of accelerating material discovery, a world limited only by the boundaries of our own creativity, supported by the tireless intellect of our artificial partners. Ultimately, the true marvel is not just the novel material itself, whether it is a revolutionary solid-state battery or a life-saving biocompatible implant. The true marvel is the binary bridge that made it entirely possible. It is the profound, evolving partnership where human ingenuity provides the vital spark, and artificial intelligence fuels the transformative fire, forging the very building blocks of our shared future together.